Now we have seen in the earlier example that the elimination order could be 6, 5, 4, 3, 2, 1, where the last entry here is equivalent to our query node XF. And we can see that this is equivalent to the marginalization in this particular elimination ordering that is stated. Well, here X6 would be the first node to be marginalized, and what it means is that this would be in the innermost of the marginalization, the summation terms in this equation here, and followed by X5, and finally we will do the marginalization over X1 last. And here we can see that by marginalizing over X6, it simply means that we can push the summation term into the factors which contains only the factors that has the random variable of X6. And once we are done with this, we'll obtain the message of M6, X2, and X5, which will pass into the next step. And then the next thing that we'll do would be to look at the innermost summation term over here, which happens to be X5, and we'll do this operation. We'll do the same thing by pushing in this summation into the factors which only consist of the random variable of X5, and then we'll compute the message of M5 and pass it to the next step. Then we'll look at the next elimination term, which is X4, and so on and so forth. So we'll at every step we will see that we'll push in the summation, compute the message, and pass it into the next step, compute the next message, and also pass it into the next step, until we finally exhaust all the summation terms in the marginalization expression. And then we will be finally left with the normalized factor over here, which we marginalize over the final term of X1. And we can also obtain the unnormalized conditional probability without the marginalization of X1. This means that we'll stop at the marginalization of X2, and this message here multiplied by P1 will give us the unnormalized conditional probability of X1 and X6, which we can then divide the two terms of the probability of X1 and X6 divided by the marginal probability of X6. And this, with this, we can obtain the conditional probability of X1 conditional upon X6. Now, the entire variable elimination algorithm for directed graph can be used without any essential change for the undirected case. And the only change that we will need is in the initialization procedures. So instead of the conditional probability that we use for a directed graph, we will now make use of the potentials, list of potential functions, which we have seen the definition in the previous lecture on undirected graphical model or Markov random field to initialize the active list. So here's an example of an undirected graphical model. Notice that there's no more edges, directed edges in this graph, and this is it becomes a Markov random field. We'll still use the same notation where the darker shading means that we have observed this node as an evidence node, and X1 over here, which remains unshaded, this is our query node, and all the rest of the nodes here would be our Newton random variable, which we denote as XR. And here it would be the same operation when we want to compute the marginal probability of X1 and X6, where we have observed X6 to be at X bar 6 over here. We'll do the same thing where it will be the same as the directed graphical model case, where we will marginalize over all the Newton random variable over the joint probability distribution of X1 to X6. So in this case here, we are going to marginalize over X2, X3, X4, and X5 over this joint probability distribution of X1 to X6. And since this is a undirected graphical model. This means that this joint probability distribution will consist of a product of all the potentials, which is written here, divided by the partition function represented as z over here. And notice that we can also use the same evidence potential notation for the observation of x6 in this example here, where we denote the observation as delta x6, comma x6 bar. So here, this case here would be where delta xi, it will still be the same thing of xi bar. It will be equals to 1 when xi equals to xi bar and 0 otherwise. And here we will still do the same operation where we will push in the summation term into the products, into the factors that consist of only the random variable that we want to marginalize over. So for example here, x6, we push it all the way in into these two terms here where it consists of only x6, where it consists of x6 in this particular two terms here. And those terms that are on the left of the summation, they will be independent of x6 and so on and so forth. So we can do this similarly. We compute this marginalization operation and we'll get a message of m6, x2, and x5, which we will pass into the next step over here. And then here we will look at the summation of x5. Since this message consists of x5, we will do a summation over the product of the potential of x3 and x5 and multiply by the message of m6. And then this term here, after the marginalization, we will call it xm5 and x2 and x3, since we are marginalizing over x5 and we are left with x2 and x3, and then we will pass it to the next term over here. And since this message over here is independent of x4, we'll pull it out of the summation sign of x4, and so on and so forth until we finally reach the marginal probability of 1, p of 1 over here. And this would give us the, so notice that this marginal probability, it's already absorbed the observation of x6 into this probability over here. Hence, the result over here, the final result here, would be the joint probability of x1 and x6, where we observe it to be at x bar of 6. We can then marginalize over x1 to get the marginal probability of x6, and this is shown in this equation over here. Then finally, we can compute the desired probability, the conditional probability, as the division of m2, the final message, which we have seen in the previous slide here, divided by the marginal probability over x6 observed at x bar 6. So what's interesting here is that the division here, on the numerator, it consists of 1 over z, the partition function, as well as the denominator, it also consists of 1 over z. Hence, we can cancel off this partition function. And this saves us a lot of computational time, because the computation of the partition function essentially means that we need to marginalize over all the random variables that is contained in the joint probability distribution. And this is going to be an expensive operation. And note that, however, if we wish to compute the marginal probability, that is to say that if we are simply interested in the joint probability of x1 and x6 bar, then what happens here, we would have to compute over the partition function, because this is simply the joint probability distribution of x1 and x6 bar is simply given by the message of m2 x1 divided by the partition function. And this is computationally expensive, this guy here, because as I have mentioned earlier, that it involves the marginalization over all the random variables. Now we have seen that the variable elimination algorithm essentially eliminates successively the number of nodes in a certain ordering given by I. And elimination here, or eliminate here, simply refers to the marginalization or removal of the node from the graph. And the final message that we have, suppose that for example, in this case that let's say we marginalize over x6 over here, and then we have two potentials of x6, x2, as well as the potential of x6 and x3 and x5, for example. So what this means here is that after the marginalization, the elimination, we are going to eliminate away x6, and the final message that we get would be m6, where we eliminated 6, the random variable of x6. But what happened next is that we are still left with a probability distribution table of x2, x3, x5 over here. And we can see that in the previous case, before the marginalization, x6 is linked to x2 here, and x6 is also linked to x3 and x5 respectively. But what this means is that x3, x5 and x2, they are not linked earlier. They are only linked, joined together to x6. Otherwise it wouldn't appear in two factors in this factorized form over here. But after marginalization, we can see that what we have done to this graph would be the case where we'll end up with a joint probability distribution table. We'll end up with a distribution table of x2, x3, x5. And what this means is that after removing x6, essentially we will have a graph of 3 nodes of x3, x5 and x2, where all these nodes are now fully connected together. So, and this process simply means that the old edges or the original edges are removed from the graph, and new edges are created and added back into the graph. So a reconstituted graph would be a graph that records all the original and newly created edges during the elimination process, which we denote as G tilde, and this consists of the original set of nodes as well as all the original and newly created edges during the elimination process. So here's an example of how we get the reconstituted graph from a Markov random field, as shown in this example here, with an elimination ordering of 6, 5, 4, 3, 2, 1. The joint probability distribution of this particular Markov random field here can be written in this way here, where we assume that z equals to 1 in this case here. And we can see that the elimination ordering starts with the random variable of x6 first. So what this means is that we simply follow the elimination algorithm, the variable elimination algorithm, as we have described earlier, where we push the summation of x6 into the joint probability distribution here, the factorized form of the joint probability distribution, where only the last two terms here consist of x6. Hence, we are going to do this operation here. And what this operation simply means is that we will start by eliminating away the random variable x6. But as a result here, we will get the message of m6. And we are left with a table, a distribution table of x2 and x5, the random variable of x2 and x5. And what this simply means is that by eliminating off the random variable x6 from the graph, we have created a new link between x2 and x5 in this particular message here. So this would be the resulting message that we get from eliminating away the random variable x6, and the graph that we are left with would be one that consists of x2 and x5 joined together in the distribution table given by this message over here. So we can look at the next step, where we eliminate the random variable of x5 over here. So in this case, we will eliminate do the marginalization of x5 over this potential of x3, x5, and the message of x2 and x5. So in this case here, we can see that we are doing this x5 summation over x5 and the potential of x3, x5 multiplied by the message of x2 and x5. So in this case, we can see that by eliminating away x5 over here, by eliminating away this guy over here, we will be left with a message of n5, x2, and x3 here. So because it consists of the random variables x3, x2, and x5 in the original summation, and finally, after eliminating away x5, we are left with x2 and x3. So this means that we have a table that consists of x2 and x3 in the distribution, in the probability distribution here. And what it means also is that by eliminating away x5, we have created a relation between x2 and x3 here. So similarly, the next step would be to eliminate away x4, and we will see that in this case, eliminating away x4 here, we don't introduce any new edges because x4 is only dependent on x2, and by doing this, we have a message of m4 and 2 here. Then so on and so forth until we have finished the elimination in this ordering. Now, if we were to collect all the original edges in the Markov random field as well as the new edges that arose from the elimination steps of the random variables, this as a result, we will get this graph over here where we see that these two links, these two edges over here, were introduced during the elimination, the variable elimination step, in particular x6 and x5. And this whole thing here, this whole graph here, is what we call the reconstituted graph. And here's the pseudocode for obtaining the reconstituted graph. We'll simply follow a greedy algorithm for the elimination in the undirected graph in the order that is given by the ordering list. And the additional edges that are added during the elimination will form the reconstituted graph with the original edges. Now we have seen that the elimination process adds new edges between the remaining neighbors of the nodes after these nodes has been eliminated. And this creates what we call the elimination clicks in the graph, or new elimination clicks in the graph. So essentially what this new elimination click means, it's referring to the message, the size of the final probability distribution table of the message that is created from eliminating a node. Suppose that we are eliminating away a node of xi, for example, so this will be mi, that message. And if this remaining message consists of many random variables inside here, or it happens that it introduces a lot of links between a lot of these random variables, then this elimination click is going to be large. What it simply means is that the table distribution, the probability distribution table for this guy over here, the new message over here, is going to be enormous, and this will introduce a lot of overall complexity in the subsequent step of the elimination, because what it simply means is that we would have to loop through every single entry in this huge elimination click or huge probability distribution table after we have eliminated away the random variable of xi. And this happens to be extremely sensitive. It's to the choice of the elimination ordering, which means that a wrong choice of the elimination ordering could actually end up with a large elimination click in the graph. And the way to figure this out, or the way to measure this, is what we call the tree width. It's defined as 1 less than the smallest achievable cardinality of the largest elimination click of all possible elimination orderings. What this means is that suppose that we have a graph with 6 random variables, as we have seen earlier on, x1, x2, all the way to x6. So this means that if I want to get the marginal probability of, suppose, x1, for example, I have to eliminate away x2 all the way to x6. And there are many choices over here. So let's say if my choice is x2, x3 all the way to x6 versus my choice as x3, x4 and all the way to x6, So these are two different choices of the elimination order. What happens here is that there is a chance that each one of these will end up to be a different reconstituted graph. And what's worse here is that it could be a case where a wrong choice of this order, for example, it will lead to a higher elimination click or higher tree width compared to the others. And this might lead to a very complex or very computationally expensive operation in the overall variable elimination algorithm. So the most desired one would be, of course, to choose the elimination ordering with the lowest complexity, that is the lowest tree width, to make sure that the variable elimination is done as efficient as possible. Unfortunately, the general problem of finding the best elimination ordering, which is to find the best tree width, to find the tree width of any given graph, is NP hard, because what this means is that we have to exhaustively go through every single combination of the elimination order and to find out what is the largest, or what is the largest elimination click over every one of these single combination of the elimination order, and this is NP hard. An example is given by the star graph over here, where we can see that the largest elimination click is actually 2, and -1 would give us the tree width that is equals to 1. And an obvious choice of elimination over this particular graph over here would be to eliminate across all these ends of the leaves of the graph. If we view this as a tree, where this is the root, and we'll eliminate via all the leaves of the graph until we reach the one that is in the center. However, we can also see that a wrong choice of this, by starting off the elimination in the center of the graph, will immediately lead to a dense connection between all the other remaining nodes in the graph. And this would lead to a high computation complexity. So it should be noted that the computational complexity of directed graphical models or Bayesian networks can be analyzed in the same way as undirected graphical models by introducing a step of the moralization, which we have seen in the previous lecture, where we marry the parents of any node during the moralization step. So given a directed graphical model, we will first convert it into an undirected graphical model by doing moralization, where we marry all the parents of every single node and dropping the direction of the edges in the graph. And then we will follow by doing the undirected graphical elimination to form the reconstituted graph in this step here. A reminder here is that in the moralization step, we are preserving the factorization of the graph, but then we are not preserving the conditional independences of the graph. So additional conditional independence might be introduced, or we might actually remove conditional independences from the original directed graph. Now here's an example of the graphical model, of the directed graphical model that we have seen earlier. The first step here towards the analysis of the computational complexity would be to moralize the directed graphical model by first marrying all the parents of every single node, and then we'll drop the directed edges in the graph. And this is a result over here where x6 consists of 2 parents. We'll marry the parents, and then we'll drop all the directions of the edges in the graph. And this would be followed by the elimination ordering to get the reconstituted graph, where we can analyze the computational complexity by looking at the largest elimination click. So we have seen that the elimination algorithm allows us to compute the marginal probability or conditional probability of a query node given a certain set of evidence nodes. We have seen this can be done by computing the marginal probability of the query and the evidence node divided by the marginal probability of the evidence node. However, there is a limitation to the variable elimination algorithm, and that is we have to recompute these steps, the marginalization step, over every set of query random variable that we want to compute. And now we'll look at the sum product or belief propagation algorithm that allows us to compute all single node marginals for certain tree-like graphs in a single run. And notice that this algorithm, the sum product or the belief propagation algorithm, will only work for tree-like graphs. That means that the graphs with tree structures, as shown in these illustrations over here. So here in the example A over here, this is an undirected graphical model, which is a tree structure without any loops. So the characteristic of a tree-like graph is that it has no loop in the graph, and every child node is only connected to one single parent node in the graph to make it a tree-like graph. And here's an example of the directed graphical model, which is a tree-like graph over here. And another special case over here would be the Markov chain that we have looked at in the previous lecture, where every single random variable simply point to the following ones. So this fulfills the two characteristics of the tree-like graph, where there's no loop and every single child node will only have one particular parent node in the graph. And here, in this case here, this is what we call the poly tree. This is not a directed tree, because if we compare this and this over here, we can see that there is a difference where after moralization, that means that after marrying the parents of all the nodes in the directed graph, we can see that in this case here, it essentially turns into the undirected tree that we have seen in the illustration here. But in this particular case, which is a poly tree, we can see that since this consists of the special V-shaped structure, after marrying all the parents, we'll end up with loops in the undirected graphical model after the moralization step. So in our study of the sum product or the belief propagation algorithm, we'll only consider this graph, and this graph, or in general tree-like graphs, where we will not make any distinctions between all these three different graphs, as we will see in the later slides. So here, let's look at the parameterization. We will make use of the undirected tree, since a directed graphical model, a directed tree, after moralization, it will turn into an undirected tree with no difference. And here we'll represent the joint distribution of Px to be equals to the 1 divided by the partition function, as well as the unary potentials. And this guy here is the binary potential, which consists of two terms. So in this case here, suppose that this is our tree. What it means here is that we are going to, for every random variable which I call xi, we are going to assign a unary potential to it, as well as the edge that links two random variables of xi and xj. We are going to assign another potential of xij to this joint probability distribution here. And we'll see that essentially this is the same for directed trees, where the joint probability distribution is given by the parent-child relation. So in this case here, this is the parent-child relation. We can see that here, suppose that I have the root node which I call xr, there's no parent to this, and for every other random variable which I call xj and xi over here, I would have the parent-child relation conditional probability, and I will have a prior distribution over xr over here. And what this means is that after converting this or moralization into the directed tree, we can see that the conditional probability here of xj conditional upon xi is essentially equals to the potential, the binary potential in the undirected trees. And in this case here, we will have the unary potential as the marginal probability of XR, where every other unary potentials of every other nodes in the graph would be simply 1. So we can see that after converting this graph, the directed tree, into an undirected tree, the two of them are actually equivalent. There's no difference between the two trees. So we'll do the analysis on our algorithm, the belief propagation or sum product algorithm, by focusing on the general form on the undirected trees. So since there's no difference between a directed tree and an undirected tree, we'll not make any distinction on these two trees, the directed trees and the undirected trees, in our discussion on the sum product or belief propagation algorithm. Here, we'll also make use of the conditioning trick, the marginalization trick, by introducing the evidence potential to make the mathematics or the algorithm elegant. In this case here, we'll introduce the local potentials to capture the conditioning of the evidence node of xe bar for some subset of the random variable xe. We'll define the local potential as this potential of superscript e over xi, and this is defined to be in the case where I is in the evidence nodes. We'll introduce the evidence potential here, and notice that we'll only introduce this on the unary term. We'll not introduce this in the binary term. The reason is obvious, because in the it's sufficient to introduce it only on one of the terms, because let's say if I have observed xi in this over here, and then I introduce this particular delta terms on xi, where in my product term, in my factorized form of the joint distribution, there might be other unary potentials that consist of xi and xj, for example. So in this case here, the summation over xi would have to be taken all together, and what this simply means is that I'm evaluating over xi equals to 0, for example, delta xi and delta, and this x bar I would be equals to 0, and phi of xi xj equals to 0, and so on and so forth. And one of the terms would be xi equals to xi bar multiplied by delta xi bar, and as well as xi equals to xi bar xj over here, and plus all the other terms. So we can see that all the other terms, they are going to drop off, because this guy here, the delta here, is all going to be 0, except for this term over here is going to be equals to 1. Hence, as a result, we can see that only this term survives this particular operation, and the result of this would evaluate to simply the unary potential taking xi bar, as well as the binary potential taking xi bar and xj over here. So hence, it's only sufficient, it will be sufficient by only representing the evidence potential in the unary term over here. And by making use of the joint probability distribution of an undirected tree, we'll get the conditional probability expression in this form over here, where we introduce the evidence potentials into the unary terms, where the original z vanishes and it becomes this particular term over here, where we introduce the delta of xi and xi bar over here, which where we call this as the evidence potential. Now, having seen the definition of the reconstituted graph, as well as the tree structure graph and its joint probability distribution, the question to ask is that what's so special about the features in this tree-like graph? In terms of the reconstituted graph, that gives us the elimination complexity, which means that by considering the structure of the graph in terms of the computational complexity, we can design an algorithm of variable elimination that allows us to perform the marginalization in a more computationally efficient way. Well, and the answer to this is that we can consider elimination ordering that arise from a depth-first traversal of the tree. We'll see that by considering the elimination ordering that arise from a depth-first traversal of the tree, we'll always maintain a tree width of 1, which is the most computationally efficient way of choosing the elimination ordering. So here, what this means is that we'll take advantage of the recursive structure of a tree to specify the elimination ordering, where we'll treat the quarry node as the root of the tree. So since we are talking about a tree-like structure, which is an example is this guy over here. So what happens here is that regardless of whichever node that we choose as the root node, for example this guy here we choose as the root node, the rest of it will automatically form the different levels of a tree. Or we can actually choose another random variable in the graph as our root node, so we can see that it will still be maintained as a tree, but in this case the tree will become an unbalanced tree. And here, suppose that we choose this guy over here as our root node, and the elimination will proceed inward from the leaf nodes of the tree towards the root node of the tree. And we can see that by doing so, the tree width, it would be equals to 1, because the largest elimination click that we'll always get would be 2 over here. Since there won't be any marrying of the parents, since every one of these nodes in the tree would only have one single parent as what we have defined earlier on. Now let us look at the variable elimination algorithm in a tree-like structure, where we'll first consider the messages that is passed between intermediate factors. Now suppose that we want to eliminate the random variable of xj when we pass this, and we want to pass this message of after eliminating of xj into the random variable of xi over here. So we'll denote this message as mji and xi, where we can see that the final message will consist of only xi, because we have eliminated away the random variable of xj over here. So this is the intermediate message that we want to pass between these two factors in the intermediate level of the tree. And we can see that within the message, we would definitely want to marginalize away xj. This is our objective over here, and we would have to consider all the potentials that contains xj, and this would be, of course, the unary potential of xj with the evidence nodes, if there's any, that is denoted by the evidence potential. And we will also have to consider the pairwise potential between xi and xj, which is this guy over here, as well as all the other messages that is passed in from the descendant of xj in the tree graph. And here we'll denote these messages that has been, because our message passing algorithm starts off from the leaves, and it gradually proceeds upward into the root nodes of the tree. So what this means is that all those descendants of xj would have already been a message after the variable elimination algorithm of the respective nodes in the descendants. So in this case, let's represent the message that is coming from a general node, which is a direct descendant of j, of which we denote as xk, where k here is in the neighbor of j. This means that it's in the neighbor of j, direct link with j, except for the link with xi, which is its parent node in the tree-like structure. And here, these are the messages. We will simply multiply all of them together with the unary potential and the binary potential, and we will marginalize away all these potentials that consist of xj and over the random variable xj. And we can see that after marginalization, we will be left with only the random variable of xi in this operation over here. And in the case where xj is a leaf node, we'll simply ignore this part over here and term it equals to 1. After looking at the messages in the intermediate nodes, we will now look at the message at the final node, which is the root node. So here, the messages that is passed to the root node, which is our query node in this case here, it would be simply the multiplication of the unary potential of the this query node xf, as well as all the messages that is passed upward from its direct descendant to the query node itself. So we'll multiply this and we'll denote all these nodes here as generally as xe, where e is in the neighborhood of f, and this means that it's all the nodes that are directly linked to this root node, which is also the query node over here. And by doing that, we will be able to get the marginal probability of xf conditioned upon xe observed. Since xe is observed, it's already absorbed into this form over here, this potential over here. Now it turns out that we only need the 2 messages to complete the message passing or the variable elimination algorithm for a tree where the query node is represented as the root node. And more interestingly, it also turns out that these messages are sufficient not only for obtaining a single marginal for a single query node, but we can actually reuse these messages that is computed in the tree for any other single marginal probability distribution in the graph. So suppose that, for example, we have computed all the messages of this the intermediate messages of mji over all the edges in the tree. What this means is that if we were to compute x1 conditioned upon xe or the probability of x2 conditioned upon xe, we can actually reuse the messages that is computed once in computing all the different marginals over the different random variables in the tree. And the key idea here is that the messages, as I've mentioned in the last slide, that the messages can be reused and we can achieve the effect of computing all the possible elimination orderings by computing all the possible messages, which is a small number. So what this means is that we do not have to repeat the message passing algorithm or the variable elimination algorithm over different marginal probability distribution that we desire. So now let us look at this example over here to illustrate how the messages can be reused. Suppose we are given a 4 random variable undirected graphical model as shown in this figure here. If we are interested in computing for example, the marginal of x1, what this means is that we would have to eliminate away the random variable of x2, x3, and x4 from the joint probability distribution of x1, x2, x3, and x4. And we have seen that in the earlier few slides that since this is a tree-like structure, what we can do here is that we can make use of this x1 as a root node, as our root nodes in the tree-like structure over here. And we can start by the variable elimination by passing messages from the leaf nodes upward to the root node. So in this case here, 3 and 4 would be the leaf nodes. And in order to do this, we would have to first compute an intermediate messages of M32 and M42 by eliminating away X3 and X4 respectively. Then finally, we will be able to compute the messages from the X2 to the root node of X1 by computing this message of M21 over here. And this is simply the product of the unary potential of X1 as well as the message after we have eliminated away X2 from the intermediate messages of X32 and X42. Similarly, we can see that in this case where we are interested in finding the marginal probability of X2. In the usual case, what we will do here is that we will marginalize away X1, X2, X3, and X4 in this particular example over here. In the naive way of doing that, what it means is that we are going to recompute every marginalization step over here. We are going to recompute the message over here. So in this case, we're going to compute M12, M32, and M42 following the last step of the messages that is passed to the root node. And similarly, if we want to compute x3, the marginal probability of x3, we will need to compute the message from x1 to x2, which we call M12, as well as M42, the message from 4 to 2. And then we'll pass this collectively into the root nodes of x3, which we consider as the root node here because this is our query node that we are interested in the marginal probability of x3. And then finally, we compute this message of M23 over here. And similarly, if we are interested in the marginal probability of x4, what we will do here is that we will compute the messages from x3 to x2 and x1 to x2. And then finally, we'll consolidate all these messages and pass it into x4 over here, which is the message of M24. And what's interesting here is that in this example of the same graph, where we want to compute the marginal probability of the respective random variable of x1, x2, x3, and x4 respectively in the graphical model, we saw that in the naive way is that we have to compute all the messages or the elimination step individually or separately over here. But what's interesting here is that we can see that some of the messages are repeated over different queries or over different query nodes. For example, in this case here, we can see that M32, this particular message, it's required when we compute the marginal probability of x1. It's also required here when we compute the marginal probability of x2, as well as here where we compute the marginal probability of x4. We can also see that x42, it's also required in the marginal probability of x1, x2, as well as x3. Similarly, the message of M12 is also repeated, is also required over 3 different marginal probability in this graphical model. And what this means is that we can actually come up with an algorithm that allows us to compute all the messages in this tree-like graph. So we are going to compute all the messages in the edges back and forth, and after we are done with computing all the messages, we can simply use these messages in computing any marginal probability distribution as we desire. And in addition to the message passing step that we have seen earlier, we introduce a message passing protocol where we say that a node can only start sending message to a neighboring node when and only when it has received messages from all its other neighbors. So what this means is that suppose I'm looking at a node of xj, and it can only start to pass the message upward to its parent node of xi only when it has received all the messages from its descendant nodes. And in order to compute all the messages in the graphical model, we'll divide this into 2 phases. The first phase would be given a tree-like structure, a tree-like graph, suppose in this case over here. What we will first do is to compute all the upward messages from the leaf nodes level by level, because we need to follow the message passing protocol where every single node can only start to pass messages upward when it has received all the messages from its immediate descendant node. And in the first phase, we'll first pass the messages upward towards the root node, which we denote as XR over here. So now in the first phase, suppose that we have already completed all this pass of the messages. Then in the second phase, we will do a downward pass of this. And what's interesting here is that suppose that we are looking at this downward pass from the root node here. We need to consider all the other messages that is pointing towards the root node except for this node itself, the target node that we are interested in passing the message itself. And similarly, let's say if I'm considering this message here from the root node to this node over here, I need to consider all the messages that is passed upward into the root node. other than this particular message that is passed in this direction here. Here's pseudocode of the sum product algorithm. First step here, which is the evidence step, is the same as what we have seen earlier, where we will add the evidence potential, denoted by delta over here, for all the random variables that are observed. And the next thing that we will do will be to first collect the messages inward or upward towards the root node from the leaf nodes. So we will do this recursively just to make sure that the message passing protocol is observed. And then once we are done with the upward collection of the messages, we'll do a downward distribution of the messages from the root node to the leaves by distributing the messages. And here's the message passing algorithm over here. And finally, once we are done with all the messages, we can simply compute any marginal probability of any random variable by making use of all the messages that we have collected in the sum product algorithm. And here's an illustration of the upward passing of the messages from the leaf nodes to the root node. So simply we'll collect all the messages, and it has to follow the message passing protocol. So when all these messages reaches this node, then we will start to send the message upward. And similarly, we'll also do a downward passing. We'll also have to follow the message passing protocol. So what this means is, in the outward passing of the messages, we'll send the messages from the root node all the way down to the leaf nodes. So in this case here, we will consider two different scenarios which we need to be careful about. So for all the intermediate nodes, because there's only one single parent of I to j, the target node of j, then in this case here, we do not have to follow the message passing protocol. But in the case where xi is the root node, for example, and this might consist of many children, where in the first pass, in the inward pass, we are passing all the messages upward towards the root node. So in the downward pass or the outward pass, if we are considering this guy over here, we would have to obey the message passing protocol. That is, all the upward passes has to be completed into this root node of I over here, or XR over here, before we can do a downward pass. Because in this case here, the downward pass would have to take all these messages in the upward pass into account, except for the message that corresponds, the upward message that corresponds to this particular edge of interest. So in summary, we have looked at the variable elimination algorithm for us to compute the conditional probability of a single random variable, and we have looked at how to explain the computational complexity of a variable elimination using the constituted graph. And finally, we have looked at the sum of product algorithm, which allows us to compute all the single marginal probability for a tree-like structure. And thank you.